Suppose we want to integrate this simple function f x y is equal to xy over the region x is greater than or equal to 0, y is greater than or equal to 0, and x plus y is less than or equal to 1. The picture of that region is, of course, I have 0 here, 1 here, this is x, this is y, I have 1 here. I have everything in here. I want to integrate that function, and that function is living on top of this region, right? So x and y take some values in this region. And the level curves will be something like, they'll actually look like 1 over x. So these are the level curves sitting above that region. We want to integrate that function. Well, using rectangular methods, it's a little confusing as to what we might do. But there's a simple remedy. Let's draw the picture a little bigger to figure out exactly what we should do. I've got this domain. What I'm going to do is I'm still going to pick a partition of x and y. So I pick a partition of x and y. And I'm going to partition from 0 to 1 still, and 0 to 1. So that means that I'm going to, in some sense, complete this square and think about the partition arising. And I'm just going to subdivide again as I would with my partition. So it's like that in the one direction, and my partition of the x's will give me something like that. And when I look at this partition, I'm only going to include in this game things that do not cross that boundary, right? So if my edge crosses that boundary, then I'm going to throw it out. So I'm just going to integrate, or I'm just going to do the Riemann sum where I include only these values, only these guys, right? And as I increase the size of the partition, that is, I refine the partition, I'm going to include more and more of the region in question. So here's a finer partition, a refinement of the partition in both directions. So we get very, very fine. And now we're going to include all the chunks now, and you'll see that not only I'm getting two things for free here. So let me do this in yellow so you see it a little better. I'm getting two things for free here, right? One, I'm getting closer to looking like the volume under the function. And two, I'm getting closer to looking like the domain that I'm actually interested in integrating over. So you notice that the steps get closer and closer to that boundary. So how would we write this as the Riemann sum? So what's the Riemann sum picture? Well, of course we have some. So let's look at our particular function in question. So 1 is less than or equal to I, j is less than or equal to n of xi star, yi star. But not only that, we have to have that xi, yi, yj is in the region, we'll call it R. So let's call this region R. So that means that the upper right corner of each block here, each little square that I'm looking at, or each little rectangle I'm looking at, is in that region. So that encodes the fact that I don't go beyond the boundary. And then of course I have delta xi, delta yi. But what if I sum over slices? How does this change? Well, if I sum over slices, I'm still going to sum over all my yj's, right? So I'm going to sum over every single yj in my partition. So this is going to be yj is greater than or equal to 0, right? So every yj that, I'm going to sum over every yj that goes above this first edge of the boundary, right? So I've got this edge of the boundary, and I'm going to sum, yj is in this direction, right? So I'm going to sum over every yj that's greater than this boundary, which is 0. And then, of course, I'm going to go to the extreme value, which is going to be 1. All my yj's have to be less than or equal to 1. So that's my outside. But when I sum over the x's, I'm going to be a little bit more delicate. So I'm, of course, going to sum over the xi's where I'm greater than or equal to 0. So the picture is I'm going in this direction and I'm summing. So let's sum over, keep y fixed, and I sum over this slice, this constant y slice. Well, then I'm going to hit this boundary. That's the x is equal to 0 boundary, right? The next boundary I'm going to hit is going to be determined by my yj, essentially, right? So in particular, I'm not going to go beyond that yj value, because otherwise I'm going to go beyond the value, or I'm not going to go beyond the value 1 minus yj, right? If I'm at a particular partition, right? So if I follow this line, so this is, say, yj at this stage, and I'm going to look here, well, if I go beyond 1 minus yj, if x gets bigger than 1 minus yj, so this is 1 minus yj, if x gets bigger than 1 minus yj, then my corner is outside of the boundary and I want to exclude it. So now this top limit of my sum is xi needs to be less than or equal to 1 minus yj. So now I have a boundary essentially determined by my y, which is constant inside of this part of the sum. And I have xi star, yj star, delta xi, delta yi. Similarly, I can do the same thing where I change the directions. So I can sum over xi greater than or equal to 0. So this is summing over every single x is equal to constant slice. X is less than or equal to 1 inside of the bounded region. Sum over, now with x fixed, yj has to be greater than 0, but yj cannot exceed 1 minus xi. Otherwise, I'm outside of this boundary. I would cross over that boundary. So xi star, yi star, now I have delta yj, delta xi. And that was simple. The sum was simple, and we also have a simple modification to the Riemann double integral over these non-rectangular regions. And so for, of course, continuous functions, on the domain R, the domain of integration, not script R, but the R from above, we have that integral over, well, let's just write it for this particular instance. We'll have integral over R x y dA is going to be, it's the integral over all y slices, right? So fix all possible constant y values. The integral from 0 to And the upper limit is now 1 minus y. It's that boundary in terms of x, right? So we solve x in terms of y. xy dx dy. And we can actually compute this thing, right? So here we just imagine that y is fixed. So this is equal to integral from 0 to 1, y integral from 0 to 1 minus y. So y is constant inside here, so we can just integrate. So this is dx dy, which is equal to, and what's this integral? 0 to 1. Well, the lower limit is 0, but let's write it all out. We have 1/2 x squared, and we evaluated the limits 1 minus y dy. At the 0 limit I get 0, at the upper limit I get 1 minus y inputted, so I have 1/2 integral from 0 to 1 y times 1 minus y squared dy. So this is going to be 1/2, so I get a y minus y cubed, and then when I evaluate that, I'm going to get a 1/2 y squared minus 1/2 or 1/4. Oh wait, but I have a square here, right? So when the square is actually out here, right? You have to be a little bit careful about that. So the square is actually out there. So you'll get minus 2y squared, so this will be minus 1/3 y cubed. And we have a coefficient of 2, plus 1/4 y to the 4th. And I evaluate that from 0 to 1. Well, at the lower limit, of course, I'll get 0, and at 1, I'll get the value, and I can calculate it, and it should be 1/24. So in general, we can write, if we were integrating over that region R, and I had some function f x y dA, as long as this was, say, continuous on that region, or just Riemann integrable, I can write it as 0, 1, integral from 0 to 1 minus y, fx y dx dy. And I can also write it as integral from 0 to 1, integral from 0 to 1 minus x, f x y dx dy, or dy dx now. In summary, we can integrate over non-rectangular regions by using nested integrals, but the only thing that changes is that the limits are now functions, and those functions are defined by the functions imposing the boundaries on the region.